Welcome to PG Pathshala, lectures on numerical methods, module 3. Today, we will be talking about Newton's divided difference interpolation, and this will be the first part of this in Newton's divided difference interpolation. The learning objectives set for today are like this. So, we will be first understanding divided differences, then we will be considering the properties of divided differences, and then we will be talking how these divided differences are used in deriving this Newton's divided difference interpolation formula that we will see. In the preamble, let me remind you that in the last module, we studied Lagrange's interpolation method, and in that method we said that the interpolating nodes we have selected were x 0, x 1, x 2, x a, x n, and it was assumed that a is less than or equal to x 1 is less than and so on and so forth. So, that means we are assuming that nodes are in the increasing order, but however, the labeling of nodes in the ascending order is not absolutely essential, and it is enough to assume that the nodes are distinct from each other. So, also nodes need not be equally spaced. So, the distance between x 0 and x 1 and x 1 x 2 all need not be the same, and they need not be in the increasing order. Only requirement is that they should be distinct. The another interpolation technique that works on unequally spaced nodes is this Newton's divided difference interpolation technique. Before we go to this, let us see what is the form of Newton's divided difference interpolating polynomial. As you remember that in the last module, we have seen the different bases for polynomials, and this different basis we have considered, and on the basis of which basis we are considering, your interpolating formula or interpolating polynomial is decided. Now, in the Newton's divided difference interpolation, we take distinct nodes as earlier, and the y 0, y 1, y 2, y 3, y n with the corresponding values of y, and to find the interpolating polynomial p x passing through the points x I, y I, by Newton's method, the following form of p x is being used. So, what is the form of p x that I am going to use is p x is equal to a 0 plus a 1 x minus x 0 plus a 2 x minus x 0 into x minus x 1. So, there will be two factors, and then finally, a n into x minus x 0 into x minus x n minus 1. These will be the n factors, and therefore, the degree of the polynomial will be n. For the polynomial space P n, we already discussed about polynomial space P n in the last module. So, what basis we are considering? We are considering the basis B 2, which was given earlier, and this basis is nothing but depending on these values. So, 1 here, 1 x minus x 0 here, and things like that. So, we will get this as basis here. The unknown coefficients a 0, a 1, a 2, a 3, a n are determined using the conditions y I equal to p x I for I equal to 0 to 1 to 3 up to n, and then using the concept of divided differences. So, what we are going to talk about is the divided differences first, and then we will come back to the formula for Newton's divided interpolation. So, divided differences are defined like this. So, again we are just repeating this, that suppose that n plus 1 points x I, y I for I equal to 0, 1 to 3 up to n are given, where they are all distinct points, numbers, and a function f represents a true relationship between x and y. Now, this true relationship may be known, may not be known, but we are just assuming that suppose that true relationship is given by f, then that is y I is equal to f x I for all I equal to 0, 1 to 3 up to n. So, then we define the 0th divided difference at node x I. So, that means this will be denoted by f of square bracket x I, and that is given by just value of the function f at x I, or we can say simply value of y I. The first divided difference at nodes x I plus 1, that is, this is first divided difference. So, for 0th divided difference I have got only one argument. For first divided difference I will have two arguments x I and x I plus 1, and we will be defining it as f x I plus 1 minus f x I upon x I plus 1 minus x I. So, that is the definition of first divided difference. and that will be valid for all I equal to 0, 1, 2, 3 up to n. So, suppose I want to take I equal to 0, I will be getting x I 0, x 0 and x 1. So, here it will be f x 1 minus f x 0 upon x 1 minus x 0, like that it will be considered. Then we consider the next second divided difference at nodes. So, again there will be 3 arguments now. So, if I consider in general, I will have 3 arguments x I plus 1 and x I plus 2, then my divided difference will be given by you take first divided difference on the last 2 nodes, and then first divided difference of first 2 nodes we are considering, take the difference of that and divide it by x I plus 2 minus x I, and that is done for I equal to 0, 1, 2, 3 up to n minus 2. So, if I want here I equal to 0, if I take, I will be getting f x 1 f x 2, that is first difference between x 1 on the node x 1 x 2 minus first difference on the node x 0 x 1 divided by x 2 minus x 0. So, this is what we will be getting for I equal to 0. In general, kth divided difference with respective nodes. So, nodes will be x I plus 1 and x I plus k. So, there will be k plus 1 nodes here, and we will be considering here f of x I plus 1. So, this is the notation for divided difference, kth divided difference, and that is obtained in terms of k minus 1th divided difference, because this will be k nodes here. So, I plus 1 to I plus k. So, for this second to last and then first to last but 1. So, that is what we are taking here, these arguments, and this will be the first divided difference minus the first divided difference over these nodes divided by last node minus the first node, x I plus k minus x I. So, this is how the kth divided difference will be defined, and that can be done for all k equal to 1 to 3 up to n and I equal to 0, 1 to 3 up to n minus k. So, given n nodes, we can have divided differences of order 1, 2 up to n, even 0th order, we have already mentioned that, and even I equal for I equal to 0, 1 to 3 up to n minus k, because kth difference will be only n minus k kth differences will be there. So, nth difference will be only 1, first difference will be n, like that we can say. The table of divided difference, this can be now evaluated from in the tabular form like this. So, I am writing these values x 0, x 1, x 2, x 3 and so on up to x n I am considering. Then I am taking 0th divided difference, that is simply value of f at this nodes. Then I am taking first divided difference. So, first divided difference will start from x 1. So, f x 0 x 1, and that can be obtained as this minus this divided by this minus this. So, that is what we will get as the first divided difference. Then here if I want to do, I will be taking x 1 x 2. So, this x 2 f x 2 minus f x 1 upon x 2 minus x 1. So, that is how I will fill up this first column, which will give all the first order divided differences. The second column will give me all second order divided differences. You can observe that it will be 1 less than the number of first order divided differences. So, I will be getting here x 0, x 1, x 2, and if I want now the value of this, I will get this minus this divided by this minus this. So, that means we get f x 1 f x 2 minus f x 0 f of x 0 x 1 divided by x 2 minus x 0. This is what I will be getting as second order divided difference, and last second order divided difference will be on x n minus 2, x n minus 1, x n. And likewise, if I complete the table, the last column will give me the nth divided difference using all n plus 1 nodes, and that will be obtained by again taking differences here and then dividing by x n minus x 0, like that we will be doing. So, this gives me the way to compute divided differences in the tabular format. Now, what are the properties of these divided differences? There are very interesting properties for divided differences. So, first property says that for distinct nodes, if the nodes are distinct x 0, x 1, x 2, x 3, x n, then f of x 0, x 1, x 2, x 3, x n can be proved to be equal to summation I equal to 0 to n f x I divided by this factor. So, what is that? X I minus x 0, x I minus x I minus 1 when there is xi here, xi minus xi will not be appearing here, xi will appear here, fxi, xi here, and then all the remaining nodes we can subtract, and you can have different factors like that, and I will be getting xi minus x 0 up to xi minus xi minus 1, then xi minus xi plus 1, this should be I plus 1, not 1 plus 1, and xi minus xn. So, that is how we will be getting, and this can be easily verified for n equal to 1. For example, suppose I want to do n equal to 1. So, what is my divided difference? f x 0 f x 1 is given by f x 1 minus f x 0 upon x 1 minus x 0. So, if I write it in this form, I will get f x 0. So, first I will be writing this f x 0, because this minus sign is there, I am changing this order of this. So, x 0 minus x 1 I am writing. So, f x 0 upon x 0 minus x 1, just as this here, plus f x 1 upon x 1 minus x 0. These are the n factors here, because I am talking about nth order difference. Because I am talking about first order difference, there are only one factor in the denominator coming. So, this is your first that means this result can be proved for n equal to 1. Similarly, I can do it for n equal to 2. For example, if I want to do it for n equal to 2, I will be getting this divided difference x 0 x 1 x 2, and then I will be getting this as, by definition I will get it as f x 1 x 2 minus f x 0 x 1 divided by x 2 minus x 0, and then that will be, if I take out x 2 minus x 0 common, and then I am writing the values of this. So, that will be f x 2 minus f x 1 upon x 2 minus x 1 minus f x 1 minus f x 0 upon x 1 minus x 0, and then if you separate out f x 0 and all that. So, if I get last value f x 0, I will be getting f x 0 divided by x 0 minus x 1, x 0 minus x 2. This x 0 minus x 2 will be coming from here, and we will be getting x 0 minus x 1. So, there is a one sign change here, this will be positive, one sign change here and one sign change here. So, that will make it all right. So, f x 0 upon x 0 minus x 1, x 0 minus x 2 I get. Then if I take f x 1, there are two terms in f x 1. So, f x 1 minus x 2 minus x 0 from here, and from here I will be getting 1 upon x 2 minus x 1 upon x 1 minus x 0. And if you simplify this x 2 minus x 0 will be cancelled, and I will be getting x 1 minus x 0, that is this factor, and this factor in the reverse sign x 1 minus x 2 I will be getting, and this will be f x 1. So, accordingly we will be getting the second term here, and similarly I will get the third term as f x 2 upon, because that is directly from here I will get f x 2 upon x 2 minus x 0, x 2 minus x 1. So, third term I get directly here. So, that is how we can prove the formula for n equal to 2. In fact, we can prove this entire result using mathematical induction. We are not going to go into the detailed proof of this. Now, we consider the second property of the divided differences. It says that the divided differences are invariant with respect to permutation of the indices of the nodes. What I mean here is that if I rearrange these nodes in any manner that and take the divided difference, that will be same as the divided difference with the nodes in the x 0 x 1 up to x n order. So, that means the order of the nodes, in which order you are writing these nodes, that does not affect the value of the divided difference, and that is evident from the first property, because in the first property we have seen here that the first property says you are summing up over all this. So, whether you write this term before or after this, the total sum will be remaining same. So, order in which the numbers these ratios are added does not matter, and therefore, your property 2 immediately follows from your property 1. So, we can get this immediately from property 1. Now, we talk about this property. So, third property we are considering. So, let A be from a b to r be a n times continuously differentiable function. Now, here we are using calculus, n times continuously differentiable function, and for some positive integer n and x 0, x 1, x 2, x n be the n plus 1 distinct numbers in a b. So, we are having this interval a b fixed, I am taking distinct nodes in n plus 1 distinct nodes in the interval a b, and for some positive integer n. Then there exists a number c belonging to open interval a b such that this f x 0 x 1 x 2 x n is equal to f nth derivative of f at the point c divided by n factorial. So, this is something similar to the mean value theorem kind of representation we are considering here. The proof of this property we are not going to go, because it will involve some calculus. So, what we will do is I will refer it to this book. You can look at the proof of this book in the book by Bourdain and Fairs, which is already listed in your additional reading material file. The properties of divided difference, we are again continuing with this. So, this is our next property, property 3 we are talking about now. We have seen property 3, and now property 3 already implies that nth divided difference of n minus 1 degree polynomial function on any n plus 1 nodes is 0. That is, if p is a polynomial function of degree n minus 1, then p nth divided difference of p, that is p x 0 x 1 x 2 x n, will be equal to 0, and this is because as nth derivative of n minus 1th degree polynomial function is 0. If you take a polynomial function a 0 x plus a 1, then in that case the first derivative will be a 0 and second derivative will be 0, and therefore, n plus first degree polynomial, second derivative is 0. So, the same thing can happen with n minus 1th degree polynomial function as well. N minus 1 degree polynomial function as well. Now, we come to derivation of Newton's divided difference interpolating polynomial, and that will be giving you this. We already mentioned that the Newton's divided difference interpolating polynomial is written in this form: p x equal to a 0 plus a 1 into x minus x 0 plus a 2 into x minus x 0 into x minus x 1 plus up to so on n into n factors like that. And it satisfies the condition that p x I equal to f x I for I equal to 0, 1, 2, 3 up to n, which yields us the coefficient. So, these conditions, there are n plus 1 conditions here and n plus 1 unknowns. So, I will be getting n plus 1 unknowns using these conditions. And how do we do that? This is done as follows. So, for example, p x 0 equal to f x 0 is my condition. So, that will imply that what is p x 0 now? If I write x equal to x 0 in p x, x minus x 0 is a factor in all the terms here, and therefore, all the terms will vanish, and I will get simply p x 0 will be nothing but a 0. So, therefore, this I get a 0, and a 0 will be equal to f x 0, but you know that f x 0 is nothing but the 0th divided difference of f at x 0. So, this I get first result as a 0 equal to this. Now, let us look at p of x 1 equal to f x 1 I am given. Now, if I substitute x equal to x 1 in this formula, then you know that second term onwards there will be factor x minus x 1 everywhere, and therefore, second term onwards everything will vanish, that will be 0, and I will be getting the formula like this, that f x 0, because a 0 is f x 0. So, I will get f x 0 here plus a 1 into x 1 minus x 0. A 0 has already been determined, and therefore, I am writing that value here. So, f x 0 plus a 1 into x 1 minus x 0, and that is given by f x 1. And if I want to calculate a 1 from there, I can look at this in a nice manner. So, f x 1 minus f x 0 upon x 1 minus x 0, this is what I will be getting. So, I will be getting this result here like this, that a 1 will be equal to f x 1 minus f x 0 upon x 1 minus x 0, but this is nothing but the first order divided difference over the nodes x 0 and x 1. So, that is how I will be getting a 1. Similarly, we can get p x 2. So, p x 2 equal to f x 2. So, one more step we will do and then we will generalize. So, p x 2 equal to f x 2 will imply what? Will imply that there will be 3 terms surviving, all other terms will vanish, and therefore, I will get f x 0 plus f x 0 x 1, because this is a 0 value, this is a 1 value, this into x 2 minus x 0 plus a 2 into x 2 minus x 0 x 2 minus x 1 is equal to f x 2, and therefore, I can take a 2 find out a 2 from this particular, because only unknown is a 2 here. So, I will get a 2 equal to the remaining terms. So, f x 2 minus these two terms there. So, f x 2 minus f x 0 minus f into x 0 x 1 into x 2 minus x 0 whole bracket, and that will be divided by the two factors which are associated with a 2. So, that is x 2 minus x 0 and x 2 minus x 1. So, we can get this, and if you rewrite this in the following form, that will give you an idea. So, what I am trying to do is f x 2 minus f x 0, I am writing it as minus f x 1 plus f x 1, just to make it in the proper format. So, that is what I will do, and this x 2 minus x 0, I am writing it as x 2 minus x 1 and x 1 minus x 0. So, and then I am going to simplify this whole thing. So, what will happen now? Let us look at this. So, f x 2 minus f x 1, and I have got x 2 minus x 1 here. So, I can take this f x 2 minus x 1, x 2 minus x 1 here, that will be this, and then this factor will be remaining. So, that will go in the denominator, x 2 minus x 0. So, that will remain as it is. So, this part is no issue at all. Now, if you look at this f x 1 minus f x 0 and this divided difference f x 0 f of x 0 x 1 into x 1 minus x 0, this factor, they are the same. So, therefore, this will be vanishing with this. So, only term will be remaining will be minus f x 0 x 1 into x 2 minus x 1. Now, x 2 minus x 1 gets cancelled here and only x 2 minus x 0 remains. So, I will get this f x 1 x 2 minus f of x 0 x 1 divided by x 2 minus x 0. This is what I will get. So, a 2 is given by this, but this according to divided difference interpolation formula, divided difference formula, I will get a 2 equal to f of x 0 x 1 x 2. So, likewise, I will get all the coefficients a 0, a 1, a 2, a 3 up to a n, and finally, I will get in general a k will be given by, which suggests now this is given by this, and it will be manipulated to get a k as f of x 0 x 1 x 2 x a. So, kth difference on the k plus 1 node x 0 to x k, and using all this I get my Newton's divided difference interpolating polynomial as follows. So, this is p x equal to a 0, that is f x 0, a 1, that is f of x 0 x 1 into x minus x 0, a 2 f of x 0 x 1 x 2 into x minus x 0 into x minus x 1, and so on, and finally, I will get f of x 0 up to x n into x minus x 0 x minus x 1 up to x minus x n minus 1. So, this is my Newton's divided difference interpolating polynomial. So, simple verification of how we have got this we have already done. Now, we take illustration 1. So, this illustration suggests that given the following data points, we want to estimate the value of y equal to 0.7. If you remember the same exercise we did for Lagrange interpolation polynomial, I am deliberating taking the same exercise, and we are trying to find out how we are going to get the values of y equal to 0.7 using Newton's divided difference interpolating polynomial. Now, this is your Newton's divided difference interpolating polynomial, because there are 4 nodes. So, the polynomial degree of the polynomial will be 3, and it will have this term. So, f x 0 plus f x 0 x 1 x minus x 0 plus f x 0 x 1 x 2, that is second difference, into x minus x 0 x minus x 1, then plus f of x 0 x 1 x 2 x 3, the third divided difference, into x minus x 0 x minus x 1 x minus x 2. So, these are the terms which we can evaluate. Now, we have to first evaluate these divided differences, and for that I am going to consider these divided differences in the following table. We have seen already that divided differences can be obtained in the tabular form, and this is what I am doing now here. So, these are the nodes x I 0.0, 0.5, 1.0, 2.0. f x I, that is the first 0th divided difference, that is just the value of the y i's. So, corresponding values of y I are 0, 0.57, 1.46 and 5.05. The first divided difference now we are taking. So, that will be given by 0.57 minus 0 divided by 0.5, divided by 0.5 is multiplied by 2. So, if you multiply 57 by 2, I will get 1.14 as my first divided difference over these nodes. Then first divided difference over these nodes, again I can get it as 1.46 minus 57 divided by 1 minus 0.5, again 0.5, and again I will be dividing it. So, multiplying it by 2. So, what is the difference I get? Multiply by 2, that I will get 1.78, and similarly about this. So, this minus this divided by this minus this, I will get this. Now, the second divided difference, if you are trying to get, what will happen now? What I have to do? If I have to find out this divided difference, I have to take the difference of this and this. So, 1.78 minus 1.14 divided by corresponding value here x 2 is 1 minus 0. So, division by 1. So, that means it will be simply division of these two, and if you look at division of this will be nothing difference of these two, and difference of these two is nothing but 0.64. So, that is your second divided difference. The third one will be given by this, again I have to take difference of this and then take difference of this and this value. So, this will be 1.5. So, I have to multiply by the difference by 1.5 and I will get this. Finally, to get this I have to take difference of this minus this divided by 2 minus 0. So, I have to divide by 2. So, whatever the difference I get, if I divide it by 2, I will be getting 0.28335 will be my final divided difference. So, this table gives me all the divided differences. We are going to use them now in finding out various degrees Newton's divided difference interpolating polynomial. So, by third degree Newton divided difference interpolating polynomial over the interval 0 2. So, what data I have to use now? I have to use here that f x 0 x 1, that is this, f x 0, that is this, f x 0 x 1 x 2, that is this, and f x 0 x 1 x 2 x 3, that is this. So, I have to use these values 1, 2, 3, 4, and these values if I substitute in my formula here which was given earlier. So, this formula, so these are the 3 values, 4 values I am getting from the table, and remaining this, if I do that and writing x equal to 0.7, will be getting your computation will be like this. So, we will getting this. So, we will get y 0.7 will be equal to 0.0 plus 1.14 into 0.7 minus 0, 0.64 into 0.7 minus 0, 0.7 minus 0.5, and plus the last term 0.2888335 into 0.7 minus 0, 0.7 minus 0.5, 0.7 minus 1, and that whole computation will amount to this value. So, which is 0.8756993. You may take approximate it as 8757. So, by now what happens at this 0.7 also lies in the interval 0.5 to 1, and now there are only 2 nodes. So, I can compute this value by linear Newton's divided difference interpolating polynomial. So, Newton's divided difference first degree Newton's divided difference interpolating polynomial will have only 2 terms, and these 2 terms will be given by what? We can see here the 2 terms will be this and this. But what is my x 0? Now, x 0 position has changed, because now I am looking at interval, one minute. So, I am looking at interval 0.5 to 1, and because I am looking at 0.5 to 1, my x 0 will be 0.5 and x 1 will be 1, and therefore, if you look at the table here, then I have to look at these 2 points. So, I have to look corresponding divided differences I have to look at. So, I have to look at this and this divided differences. So, these are the rate data I am going to get. So, this rate data I am going to consider as 0.57 into 1.78, and that is what I am going to use in order to evaluate this. So, you can see here by a linear difference interpolation 0.57 1.78 into 0.7 minus 0.5, and if you take this it will be 0.926. So, which data I am using? Using rate data from the table. So, table has been colored because I just wanted to show that which data we are using in the corresponding computation. So, here we are using green and yellow, here we are using red data. And similarly, I can also think of that 0.7 also lies between interval 0 to 1 as well as between 0.5 to 2. So, if I use these first three nodes and then last three nodes, I can get quadratic Newton's divided difference interpolating polynomial. And this by quadratic Newton's divided difference interpolating polynomial over interval this, using red and green data, we have to use red and green data from the table, because if I have to use quadratic polynomial, I will need 3 terms. So, which values I am using? Now, 3 terms I am going to use are this 0, 0.5 and 1. So, I will be getting the differences like this like that I am going to consider. So, I will be using these 3 values, and we will see here quadratic polynomial. Oh, I am going backward instead of forward. So, we get here 0.0, 1.14 into 0.7 into 0, 0.64 into 0.7 into 0 into 0.7 into 0.5, and I will get this value. And if I use this interval, again I have to take last 3 and then corresponding differences. So, I will be using 0.57, 1.58, and that we can see from the table again. You can see we are using these 3 nodes. So, we are using these 3 values. So, red and blue data I am using. So, I am using these 3 values. So, that is how we will be getting the last computation here like this 0.57 plus 1.78 into 0.7 minus 0.5, 1.2067 into 0.7.5 into this, and I will get that value as my estimate of y. So, different degree interpolating polynomials will give you different values. Now, if you plot these polynomials on the entire interval, it will look like this. So, this gives me linear interpolation, and that will be observed only in this interval 0.5. So, there will be 0.5 here, 0.5 to 1. So, in that interval there will be straight line, you will see here, there is a straight line here. Then quadratic will be, one quadratic will be between 0 to 1 and another quadratic will be 0.5 to 2, and that will be. So, there will be 2 curves like that in this color. So, one is green and one is blue, and the cubic will be on the entire interval, that is given by this. If you look at this, that smallest interval here is 0.5 to 1. So, if I restrict my graph to this smaller interval, then it will give you clear cut picture as to what is happening. So, this is my 0.5 and this is 1 actually. So, 0.5 to 1. So, you can see that linear quadratic will be given by this particular line, that is linear. Then there are 2, there will be quadratic here, green quadratic I will be getting, and then there will be this one, another quadratic will be given by this blue color, and then the cubic will be magenta. So, that is how I will be getting various values, and here I have written down those values of x equal to 0.7, what are the values of y according to this 4 different polynomials is indicated by these points here. So, there is 1.9. So, on linear it will be 0.926, on quadratic it will be this, and then on cubic it will be this. So, that is how we can get all the desired computations and shown on this graph. So, in summary, we can understand that in this module we have discussed divided differences and their properties, tabular procedure for computing all order divided differences, then derivation of Newton's divided difference interpolation polynomial, and we have given some illustration and graphical comparison of Newton's divided difference polynomials of various degrees. Thank you.